we're going to continue to strengthen the topic that we have learned this morning. For today, I'm going to do few example to cover the subject that we have covered this morning. Okay, so tonight we're going to do 3 to 4 examples. Okay, within this 1 hour. First thing, we cover the topic of the example of 11.3. Okay, and we'll go through this example. Okay, this example. We are referring to this example. This morning I have talked briefly about how to solve this problem. So in order for us to solve this problem, we have to solve it. Number one, we need to write B in term to write B part A, we have to write B. Okay, B in term of okay, in term of B. Okay, so we substitute minus KB for A in the fundamental formula defining by acceleration. Okay, acceleration we have A equal to dV dt. Okay, okay, A equal to dV dt. So what you need to do here is you put everything together. We have a minus KB equal to dV dt. Okay. Okay. So you put all together dV and V. So you have dV over V. Okay. And then minus K dt. Okay. Minus K dt. Okay, minus K dt. Okay, so minus K dt. Minus K. Okay, minus K dt. So what you need to do then? After that, we have to integrate both sides. Okay, integrate both sides. Okay, integrate both sides. Okay, we integrate both sides. Alright. When you integrate both sides, you are going to get natural log. This one you integrate dV V over V. So you are going to get natural log. Okay, natural log to get natural log. Oh, my pen jump here and there. Okay. To get the natural log. Okay, we get natural log. Natural log we use mouse. Easy. Divide by v equal v dot. Okay, equal to minus kp. Okay, minus kp. Okay. So we can write this one in terms of exponent. Okay, so when we write in terms of exponent, when you write in terms of exponent, you're going to get v, okay, equal to v dot v equal to v dot, okay, exponent e to the power of kt. Okay, so you can to get this. So this is for the first part. Okay, okay, this is a natural log. Natural log. Okay, natural log. Natural log b over v dot. Okay, so this is for the first one. Okay, this is for the first one. That is for part A. We have done doing part A. Okay, for part B, we need to write. We need to write to find what? We need to find x in terms of p, right? So that is for part B. Okay, we have done part A. Okay, this is for part B. For part B, we have to write x. Have to write x in term of p. Okay, so write x in term of p. Okay, for x in term of p. For this one, we have to substitute the expression, okay, that we have just obtained, okay, for v into v equal to dx dt, okay, v equal to dx dt. Okay, so we have obtained the value that we have obtained just now, which is here, okay, v. This is v, the one that we obtained just now. So we write by using this relation. So what you're going to get here is we get this value v equal to, okay, v equal to v dot e to the power of minus kt okay, this is the x and this is okay, this is v equal to dx dt. Oh, my point, my pen keep jumping. Sorry about this one. Okay. Okay, so we have the value of dx dt. You can write dx dt. Okay. So v equal to dx dt. Okay, this one better. Okay, so we have to take this one, which is this one. So this is b dot e to the power of minus kt, kt, and then we equate it to be dx dt. Okay, we equate this one to be dx dt, and then we put, okay, we cross multiply, okay, and do the integration. So we get the integration of 0 to x, okay, 0 to x dx equal to v dot, okay, and then from 0 to t, and then this, which is e exponent minus kt, okay, dt, okay, kt dt, all right. Okay, after that, when you do the integration, okay, so you're going to get x, okay. We integrate this one, so you get x, okay. So we get x, okay, x equal to minus b dot, okay, minus b dot k, all right, and then you multiply by e to the power of minus kt, okay, and then you solve the limit from 0 to t, okay, and then you get the value of minus b dot over k, okay, b dot over k, and then e to the power of minus kt, okay, minus 1, okay. So you can simplify it to make it positive, okay, so it's going to be positive, so positive v dot over k multiplied by 1 minus e to the power of k, okay, all right. So that is part B, okay, part B. Now we move to part C, okay. So for part C, okay, I'm going to erase all of this, okay. So for part C, you have to write v in terms of x, okay. Okay, so you write v in terms of x, okay. So how to write b in term of x? Okay, we want to write b in term of x. Okay, so we start by writing, we substitute minus kb for a, which is in this case a equal to, remember the term v times dv dx. Oh my point keep jumping again. Okay, I get this again. Alright. Okay, so we start by writing a equal to v dv v dv, okay, v dv dx, yeah? Okay, alright. So acceleration equal to v dv dx. Okay, so you put everything together. Okay, put everything together. So we're going to get minus kv equal to v dv dx. Okay, dv dx. So you take dv. Okay, dv equal to minus k dx. Okay, so you integrate both sides. Okay, integrate both sides. V dot, okay, to v. Okay, and then this minus k, 0 to x. Okay, so what you're going to get is v dot, v minus v dot equal to minus kx. Okay, yeah. Okay, and then you solve the value of v. Okay, so you get v equal to v dot. Okay, v equal to v dot minus kx. Alright, v equal to v dot minus kx. Okay, so this is the answer for part A, B, and C. Okay, this is an example of example 1.3. Okay, example 1.3. Okay, we have done doing this example. So the thing that I would like to highlight is, in a nutshell, is we solve this problem. First part, we find velocity in term of t, and then part B is x in term of t, and then part C is v in term of x. Okay. Okay, we have done this example 1.3. Now we move to other example. Okay, other example. Okay, other example from your textbook. We, we do this example. Okay, refer to your note. Example 11.10. Okay. All right. So in this problem, we have to find what will be the acceleration of the automobile. Okay, of the automobile. Okay, immediately after the brake has been applied. Okay, so as I said, you need to find here is a tangential component of acceleration. Okay, and then you have to find. Okay, so the strategy to solve this problem, number one, you have to find the tangential component. Okay, of acceleration. So tangential acceleration. Strategy number two, you have to find the normal component of the acceleration. Okay, and then number three is you have to find the magnitude of it. Okay, which is a total. Okay, which is a total. So before we proceed, what I have mentioned this morning, we need to do the conversion. We have to convert miles into feet per second. Okay, so convert miles into feet per second. Okay, because we want to get the value of in feet per second. So do the conversion. Okay, so how to do the conversion? Okay, how can we do the conversion? We do the conversion. Okay, for British system, the speed. Okay, we need to express this the speed to be in feet per second. Okay, so we have here to do conversion 60. Okay, 60, 60, alright, 60 mile per hour. Okay, mile per hour. Okay, how to do the conversion? 60 mile per hour. Okay, 60 mile per hour. Okay, okay, how to do the conversion? Okay, 1 mile, okay, equal to 5,280 feet. Okay, 1 mile equal to 5,280 foot. Okay, and then for 1 hour, you have to convert. In 1 hour, we have 3,600 seconds. Okay, so we do the calculation. 1 mile, we eliminate this one. Okay, 1 hour, we eliminate with hour. And then the only remaining unit we have here is in feet per second. Okay, feet per second. So you multiply 60 times 5280 divided by 3,600. So you get 88. Okay, you get 88, 88. Okay, feet per second. Okay, we get 88. This is how we do the conversion. Okay, that's how we do the conversion. Okay, that's how we do the conversion. We get 88, 88 feet. Okay, 88 feet per second. So this is the first step. Okay, same thing for 40 miles. 40 miles per hour. Okay, we have done this one for 40 miles per hour. 45, sorry, 45 miles per hour. Also, we do the conversion and then we get 66. Okay, 66 feet per second. Okay, so this is the first step that you need to do. Okay, what's the information that we have in this problem? It's mentioned that the motorist, okay, decelerate. Okay, so meaning the automobile slow down. It slow down at a constant rate. Okay, so we have to find the average acceleration. Okay, so by definition, remember, by definition, average, we have average acceleration, which is average, okay, average AT, okay, average AT is denoted as delta V divided by delta T, okay. Okay, this is the definition of average. Average acceleration, okay. We have average acceleration, okay, average acceleration, average acceleration T, so you get 66 minus 88, 66 minus 88, okay, divide by 8 seconds, okay, because after 8 seconds, so 66 minus 88 divided by 8 seconds, so you get minus 2.75, okay, minus 2.75 feet per second, okay, feet per second square, okay, all right. So this is the value of average acceleration, okay. Okay, so we have done the first part, which is this one, okay, AT, okay, average acceleration, and then we proceed to find another one. So we have done this one. Now we want to find the normal acceleration. So immediately after the brake, the brake has been applied, okay, the speed, okay, the speed still 88 feet per second. So therefore we're going to have, so allow me to erase this one. We proceed to part 2 now, which is part B now. Okay, for part B, we talk about normal component. Normal component acceleration. Okay, so we find AN equal to V square over rho. Okay, so in this case, I have told you just now, the velocity, okay, after the brake has been applied is 88, still 88 feet per second square. Okay, make sure you write the right unit. Okay, so 88 square, put all together, 88 square, divide by rho. Okay, so rho is this one, which is 2500 feet, 2500 feet. Okay, 2500 feet. So we have here 88 square divided by 2500, 88, 88 square divided by 20. Oh, keep jumping. Sorry, my pen now keep jumping. Something wrong. Okay, this one. Okay, so we get AN equal to 88 square, 88 square, 88 square divided by 2500. 2500. Okay, so you get 3.10, okay, feet per second square. Okay, right? So we have done the second part of it. Okay, this is a normal acceleration, 88 square divided by 2500 feet. So you get 3.10 feet per second square. Okay, okay, this is the last one for part C. Okay, so part C, okay, for part C, we want to find the magnitude of it. Okay, what will be the magnitude? Okay, so for magnitude of it, I'm going to proceed. We're going to refer to the figure here. Okay, this is the magnitude of it. Just now you have obtained normal acceleration. Okay, this is normal acceleration that we have calculated. Okay, earlier, which is it is in this direction. Okay, this direction, which is 3.10 feet per second square, right? And then you also have calculated tangential component of acceleration, which is pointing to this direction, tangent to the path, okay, which is 2.75 feet per second square. Okay, now you have 3.10 normal acceleration and tangential acceleration. Okay, so what you need to do then? For part C, okay, for part C, we need to find the magnitude and the direction of acceleration. Okay, magnitude and acceleration and direction of the resultant, direction of acceleration. So this is alpha. Okay, so tangent alpha. Okay, tangent alpha. Tangent alpha. What is tangent alpha? Tangent alpha is equal to normal acceleration divided by tangential acceleration. So you obtain 3.10 divided by 2.75. Okay, so unit is feet per second square. So up and down divide. So equal to that value, and then you find the inverse tangent of this one. So you obtain alpha is 48. Okay, 48.4. Okay, 48.4. And then we want to find acceleration equal to an divided by sine alpha. Okay. So what is an? An is 3.10. Okay, 3.10. The unit is feet per second square. Divide by sine 48.4. Okay. All right. So therefore, acceleration is equal to 4.14 feet per second square. Okay. Okay, this is an example 11.10. Okay. So our next example, which is example 11.12, relate uh, to color problem. Okay, color problem. We have to refer to example 11.12. Okay, you can refer to your class note. Okay, for this one, right? 11.12. Okay. So again, for this problem, part A, you have to find the total velocity of the collar. Part B, total acceleration of the collar, and then the relative acceleration of the collar. Okay. Yeah. So we start with the first one. Okay. First thing, Okay, first thing we have to do is uh, the first thing we have to do is you are given the keyword here is 30 degrees. The arm has been rotated at theta equal to 30 degrees. So this 30 degrees you have to convert, okay, theta equal to 30 degrees, okay, convert into radian, you get 0.524 radian, okay, 524 radian. This is the first part. So we have to look at here, okay, the expression of theta, okay, this expression of theta is theta equal to 0.15 p square, okay, all right. So we know that theta, this is in radian, is 0, so substitute here, theta 0.524 equal to 0.15 p square. So solve for t, okay, so you get t equal to 1.869 second, okay. So this is first thing that you need to do. And then you need to write equation of motion by substituting the value of t, okay, for r, for theta, okay, okay, for their first and second derivative, okay. So you have, we start writing this one, which is a radius r and then theta. So you write this. So we want to write r, we want to write r dot, we want to write r double dot. Okay. Same thing for the your right, like okay, for the theta value. So you have theta, theta dot, and then theta double dot. Okay. So you need to write this term and then you differentiate with respect to time, okay, with respect to time. So start with this one, r is 0.9 minus 0.12 t square, okay. So you differentiate with respect to time, you get minus 0.24, okay, minus 0.2424 t. Okay, and then you differentiate another one, you get minus 0.24. Okay, minus 0.24. Okay, and then for theta, theta is from here minus 0.15 t. Okay, you multiply by, okay, 0.15 t. You didn't multiply by value 1.869 yet, so you have 0.15 t square, okay, and then you differentiate, you get 0.3 t, okay, and then you get 0.3, okay. Okay, don't forget the unit, okay. This one is in meter, this is meter per second, this meter per second square, and this one radian, radian per second square, okay, the unit, radian per second square, this is radian per second, this is radian, okay. So you multiply this theta with 1.869 and then you get the value, okay. So this is what we call equation of motion. All of this we call equation of motion, okay. Equation of motion, equation of motion, okay. These two we call equation of motion. All right, this is the first part. So I recap what I have done. First of all, you have to convert the value of theta in terms of radian, and then you solve uh, this basic equation and obtain t in second, and then you put uh, these two terms together, which is r and theta, and then you differentiate with respect to time, right? You differentiate with respect to time. Okay, and then after that, we substitute the value. Okay, and then we obtain the value of theta, theta dot, theta double dot, r dot, and r double dot. Okay, that is the first part. We write time at theta equal 30 in radian. And then part 2, we write equation of motion. Okay, after that, now we are ready to solve the problem. Okay, the first part, which is part A, we want to find the velocity of B. Okay, now we want to find the velocity of B. Okay, so I erase all again. We want to find the velocity of B. We want to find the velocity of B, which is part A, velocity of B. Okay, velocity of B. So how to find velocity of B? Remember equation that we have written earlier. Okay, you wrote down in your formula sheet. Okay, which is equation of radial and transverse component for the velocity and acceleration. Still remember? Do you still remember? For the velocity, we have V equal to r dot unit radial plus r theta dot, right? And then unit transverse. Okay, unit transverse. So for here, we know that if we write VR, we have r dot er. Yes, this is very important. Okay, so go back to this one. All right. So we have VR equal to, okay, this is VR. VR equal to r dot. Okay, r dot. And then what is V theta? V theta is equal to this one, which is r theta, r theta. Okay, so you substitute the value of it. Now you can substitute the value of it. Okay. Okay. So you have equal to r dot, which is minus 0.0449 meter per second. Okay, and then for V transverse, which is r theta dot, so you get 0.481. Okay, 0.481. Okay, multiplied by 0.561. Okay, so you get the velocity of 0.270 meter per second. Okay, this is the velocity, okay, of VR, okay, and the velocity of B theta. Okay, okay, okay. So we have VR, which is this one, and then V theta. Okay, so V theta VR is minus 0.49. Okay, do a correction again here. Okay, VR is minus. Oh yeah, V theta. This is V theta. All right. VR is minus 0.49, and then okay, V theta, which is this one, equal to 0.270. All right. Okay, this is 0.270. All right. So this is part A. For part A. For part B, we have to find the acceleration. Okay. All right. For the acceleration, okay, I erase this one. Let me erase. We move to part C. Okay. For part B, we want to find acceleration. Okay. Just now we have obtained velocity of B. Now for part B, we want to find acceleration. Okay. Acceleration. Okay. Acceleration of B. Okay. Again, we have to use the equation that we have obtained earlier. Okay. So we know that the formula for acceleration, radial acceleration is R double dot minus R theta dot square, okay, and then A transverse equal to R, okay, plus 2R dot theta dot, okay, 2R dot theta dot. This is 2R dot theta dot, okay, theta dot. Oh, big jumping again. Okay, 2R dot theta dot. Okay, 2R dot theta dot. 2R dot theta dot. Okay, so these are two important formula. You can refer in your textbook for these two important equations. Okay. Okay. So make sure you write it correctly. This is 2R dot theta dot. Okay. Yeah, 2R dot theta dot. A transverse equal to R theta double dot plus 2R dot theta dot. Okay, this is what. Also for AR equal to R double dot minus R theta dot square. Okay, so this is what we call the scalar component for radial and transverse direction. So we need to use this equation to find the acceleration. Okay. starting by finding AR. Okay, so you substitute R double dot, the one that you have differentiated just now, which is minus 2.40, okay, minus 4.81 times 0.561. So you get the value. Same thing for this one, you substitute the value. And then you have obtained the value of for both, okay, for both, which is I take this one as an example AR, which is minus 2.40, okay, minus 0.481 times 0.561 square, okay, so you get the value of minus 0.391 meter per second square, okay. Okay, so this is the answer for radial acceleration. Same thing for transverse. Okay, so you get AR minus 0.391. So for A theta, okay, for A theta you get, to substitute the value, you get 0.359. Okay, the unit is meter per second square. Okay, all right. So this is the value AR, and then you get here A theta and AR. Okay, last one. Okay, last but not least, what will be the acceleration? Okay, the acceleration of B with respect to arm OA. Okay, so we refer to the figure. Okay, we refer to the figure here. Okay, for this one, we refer to the last figure here. So for part C, basically, we want to find acceleration of B with respect to arm OA. This is arm OA, okay, acceleration B. So this collar keep moving, okay, up and down. So basically, motion of the collar with respect to the arm is rectilinear, okay, rectilinear, and is defined by coordinate R. Therefore, we have obtained here AB relative to OA basically is R double dot. So what is R double dot? We have differentiated just now. We obtain the value of minus 2.40 meter per second. All right. Okay, that's all for tonight. Okay, I hope you can go through the example, other example in your class note. Okay, and also if time permit, you can find a textbook, okay, written by Beers and Johnson. Okay, try to do familiarize yourself with all of the example in our in the textbook, so that it's easier for you to do revision and doing your quiz and test it and the final ODL test later on. Okay, thank you. So I'll see you next in our next class on Friday.
Welcome, Doctor. Thank you.
Thank you, Doctor.
Thank you, Doctor.